In our 2 hours together, we're going to do a lot today. So the last 2 hours we took the Schrödinger equation and we solved it for central potential, or in other names, a hydrogen atom. We had a positive charge at the core, we have an electron, it feels a coulombic force, it's spherical. So we solved, or at least we wrote down how to solve Schrödinger's equation for this potential. And we looked at the angular solutions last time round. We managed to split our equation up into a radial equation and an angular equation, separate those two out. And we solved for the angular part, or at least we wrote down what the solutions were, these things called spherical harmonics. Go and look them up in a book, you'll find big lists of them. And drew some of them down, and you get nice shapes. And the shapes might be familiar to you if you've done A-level, whatever, physics and chemistry. So today, and then we started to look at the radial equation, and we made a guess about the shape of a radial wave function. We guessed it was AE to the minus R over A naught, and we showed that that was indeed a solution to the radial wave function. It is an eigenfunction of that operator. So today we're going to take that a little bit further. We're going to normalize it to begin with. Then we're going to look at what we can say about what is the chance, what is the probability of finding an electron some distance from the nuclear core, or the proton as it is. What is the radial probability distribution, which will tell us something about the size of an atom. If you look at the bottom of all your sheets, there's on the bottom left-hand side. So by the end of today, you will know what these things are, hopefully. They're there for a reason. And then we should get on to looking at the full solution. So we're going to bolt together the radial wave function with the angular wave function, multiply them up, and that gives us the full wave function. So we'll look at those for hydrogen. And then I think we should get on to energies, looking at atomic spectra and what we can say, how we can actually measure these things. But we will start with normalization. So at the end of when was yesterday? Thursday. End of Thursday. We had written that the ground state was this thing here. The ground state wave function was E times the exponential of minus R over A naught, where A naught is Bohr's radius. So we need to normalize this. Basically, what we need to say is the total probability of finding the electron anywhere must be unity. Square of wave functions gives you the probability of finding an electron there. So we know that we've only got one electron, so the chance of finding it anywhere in the universe must all add up to 1. It's normalized. So we need to calculate this. So we're going to calculate this overlap S, which is just the square of the wave function. So we're going to take the complex conjugate of the wave function psi with the wave function, and we're going to integrate it over all space. That's all we need to do. Psi star psi. So we're working in spherical polar coordinates with r, phi, and theta. Can you actually read any of this? That's better. In which case, we need to know what the limits are for each individual term. So we can integrate r from r equals 0 to r equals infinity. We can integrate theta from theta equals 0 to theta equals pi. And the phi term has to go from phi equals 0 to phi equals 2 pi. Basically the limits that we wrote down before. Then we have psi star psi, take the complex conjugate. And we have this term, r squared sine theta. So this drops out of considering what small volume at some distance really is equal to. Have you done r squared sine theta before in your mathematics? No. Hand up if you have. If r squared sine theta is vaguely familiar, because I'm not actually going to derive where it comes from. But eventually you will come across where it comes from, or look it up on Wikipedia and you'll find out where r squared sine theta comes from. It's not very magical, it just takes time and it's a bit messy and it's not core to this course, but you can look it up. So if we do all the angular integrals, which you can do at home, that comes out to be 4 pi. That's nice easy. And then we just need to do the other integral, and we know that it's all got to equal 1, because we've got normalized, it's all got to equal 1. This whole thing's got to equal 1 because it's normalized. The total probability of finding my electron anywhere is going to be 1. And if you do all the mathematics, which I'm going to leave you to do, we can work out what this prefactor is. So I can write down my full wave function there. for the L equals 0, M sub L equals 0. And it's 1 over the square root pi A naught cubed e to the minus r over A naught. It's beautiful, simple expression. This is the wave function for the ground state electron in hydrogen. This will tell us the energy of our electron. In a couple of lectures' time, this is going to tell us the total angular momentum of our electron. In a couple of lectures' time plus 1, this will tell us the projection of the angular momentum onto the z-axis of our electron. Anything we ever wanted to know about our electron is actually buried inside here. This is going to tell us everything we could ever know about it, apart from spin. There's nothing to say about spin, we'll get to spin. So that's nice. So what we can do is we can use this to say something about what's the chance of finding the electron at some distance away from our central hydrogen core. So what we can do is we can look at the probability density. As you have done many, many times in all the quantum courses you've done, we just square the wave function, which is all I did up at the top. I just squared it and then added up all the different bits. So we square it. I'm just going to leave this as a squared for the moment because I can't be bothered to write down all that. And then we have e to the minus 2 r over A naught. So it's a complex conjugate times the wave function. But we don't have any complex numbers, so it doesn't matter in this case. And we end up with 2r over A naught. So we can draw this. What does this look like? So on the next page, let's draw a picture. So we're going to have two axes. The first one is going to be the wave function squared. And the other axis is going to be the radius in units of A naught. So let's do 1, 2, 3, whatever, 4. So 1A naught, 2A naught, 3A naught, 4A naught. So we can now sketch this using our amazing powers of sketching. So it's going to start off at A squared, and it's going to exponentially die off all the way down there. So that is what the square of the wave function looks like. Just drawing that function. A squared e to the minus 2r over A naught. So then I can ask the question, where is it most probable to find my electron? Hands up if you think you know the answer to where is it most probable to find my electron. That's a few hands. Hands up if you don't know where it is most probable to find my electron. Or indeed your electron. Hands up if you have not put your hand up. Okay, well at least you can follow logic. So naively, you think, well, the most probable place to find my electrons at the core. R equals 0. I have this massive spike. That's where I'm going to find it. The electron mostly hangs around the core. And you should all be thinking, no, that's crazy. One of the whole things about quantum mechanics is people couldn't figure out why electrons didn't fall into the core. You've got this positive thing, you've got this negative thing. Classical mechanics says they should just stick together. And you end up with the plum pudding version of nuclear physics. So this is sort of suggesting that that might be true. But we are forgetting something, or at least the ones who put their hand up first were forgetting something. This is in fact quite misleading. So what we really got to do is we have to consider what is the probability of finding an electron in a small volume dV. Just asking the question, what is the probability at a single point of finding the electron doesn't really make any sense. What we need is a small volume. What's the probability of finding it in a small volume? That's the real question. So what we really want to consider is psi squared dV. Just the same with any probability distribution, you always end up with the probability distribution and a little width, never just the probability distribution all by itself. So we're going to define something, which we're going to draw in a minute. called the radial probability distribution, and we're going to call it P of R. So what is P of R? What does it actually physically mean? So P of R dr, it's the probability of finding an electron between a radius r and r plus dr. So it's no longer a fixed sum position, it's now at any radius r and r plus dr. So that's good. So what we need to know is, what is this dV thing? So it's, all it is the volume of the shell between r and r plus dr, which we'll just, I'm going to put, now I'll draw a picture of it. So we've got x, y, and z. So what we're saying is we've got some sphere at radius r, and I have another sphere very slightly bigger, infinitesimally bigger, which has got width dr. So that's two shells, and I've got some volume in between them. If you've ever integrated up space to find the volume of a sphere, this is just the same tricks. So we can work out what this volume is. What is the volume? Well, it's just the area, which is 4 pi r squared, times the thickness, which is dr. I've done this backwards for some reason. So it's 4 pi r squared dr. That's the volume of the sphere, of this shell. Just the area of the shell times the thickness of the shell. Which means that I can now work out what the radial probability density is. So it's the probability of finding an electron at some distance r times the total volume at that distance r. It's kind of like a waiting time. So as you get further away, the probability drops off because this wave function dies off exponentially, but there's more and more space in which to find your electron. So we multiply these two together, we get that the radial probability distribution, this thing P of R dr, is my wave function squared times the volume 4 pi r squared dr. And that really reflects the probability of finding an electron at some distance r. So let's plot it. Don't turn the page, go back up. Let's plot it up here. Another axis. So now let's plot P of R. Brought my own red pen today. So we have psi squared, which is this exponential decay, but we also have an r squared term. So r squared, that small r is small. R squared is going to get bigger and bigger and bigger and bigger and bigger, but eventually this exponential term is going to take over. But I know what it looks like, so I'm going to draw it. Let's see if I can do it properly. It's going to go up because of r squared, and then it's going to come back down again, and eventually it's going to look like a decay. Because we live in three-dimensional space. So even though the wave function is maximum at the hydrogen nucleus, there's only one tiny bit of volume of space. There's only one little tiny box dV. If you imagine you've got a little box, so you've only got one of these, whereas if you go a little bit further out, you can pack up many, many of these boxes. So the total probability at that distance is the probability of any one box, which is going down and down and down and down and down, multiplied by how many boxes you have, which is going up and up and up and up. So you end up with this peak at r equals a naught. That's the most probable place to find my electron. So it doesn't actually really ever get to the nucleus. It gets stuck at some distance. You're not likely to find it out here. So if we take an example, can someone in the back row stand up? Anybody? One person? You, because you just made it. Oh no, excellent, you've made it. So You've got an electron somewhere. Can you point to one of your electrons? You're pointing to your electron over there. That's highly unlikely. Point to one of your electrons. Right, there. Excellent. So the probability of finding it near you, so A naught is quite small. It's like 10 to the minus 11 angstroms. No, 10 to the minus 11 meters. So the probability of finding that particular electron over here, we have to go all the way out here. Is it 0? No, it's not. It's a small number. In fact, there's a probability of finding that particular electron anywhere in the universe, which should worry you and is a bit crazy, but there you go. Thank you very much for you and your electron. I appreciate it. Right. So we can write the whole thing for the ground state now. I think I did actually watch a whole hour of Brian Cox talking about that effect. We are all connected with the universe, all electrons are connected with every other electrons because all we have is exponential decays, but we'll just do it in 2 minutes. So we can write this whole thing for the ground state as a squared 4 pi r squared e to the minus 2r over a naught dr. Don't know why that dr is there. Let's get rid of it. So again, I could plug in what a squared is, but I can't be bothered. So that's what we've just drawn. We've got this 4 pi r squared term which describes space, getting bigger and bigger and bigger the further we go away. But we've also got the wave function dying off exponentially. So we have a competition between these two, which gives us our shell-like structure. So what can we say from all this? You're most likely to find the electron at r equals a naught. That's the most probable place you can find your electron, and that's problem number P6 or 7 or something. So the wave functions have a maximum at the origin, but because we live in three-dimensional space, there's little chance of actually finding the electron at the nucleus. So it's this competition. Now it's very easy to get very confused about all these things and realizing that you're doing it in R or it's dr or it's phi and theta. But after a while, with some cool thought, you can generally work out which place you should be. So as you get further away, the probability drops exponentially towards 0, but it never quite gets there. Hence, any electron that you own at the moment can be found anywhere else, and anybody else in this room or anybody else on the campus or anybody else maybe in Bristol or anywhere in the universe. There's a small probability of it being there. It's good, eh? But luckily it's pretty small, so they mostly stay bound to you. So you don't have to worry about it too much. Okay, good. So now we've done angular stuff, radial stuff. Let's plug them all together now. So we separated them out to begin with. Oh no, sorry, no, we're not going to do that. We're going to look at all the other solutions. So we had this radial equation to begin with. And we said, let's assume L equals 0, and let's guess a solution, and it seemed to work. So we've solved for the ground state, L equals 0, but you can in fact solve for L equals 1, L equals 2, L equals 3, 4, 5, 6, 7, all of them. So we can solve this for any value of the quantum number L. And these again are a family of functions, so we're going to write down the first few that we're ever going to play with. If you want to look it up in a book, there's an infinite number of them. So what do we need? We need solutions that are finite between r equals 0 and r equals infinity. Otherwise, we don't have well-described wave functions. We can't normalize them. And we're going to end up with an integer n, where n is less than L. So we're going to end up with radial wave functions that are described by two integers now, n and L. So they tell us which bit of the book to look up. Oh, scheiße. It is less than. Oops. Thank you. So What we need to do is we've got a big book of these things, and we can look it up based on its n and l values. And then we pick that one out, and that's the one that will solve, that's the eigenfunction. So we label them R, n, and L. Yes, he's right. You're wrong. I'm right. So what we need to do is underline. Let's just do it all again. N is greater than L for R. I'm glad someone knows what they're doing. I get paid more than either. So let's draw them. Let's write them all down. I'm sure there's a class I can go on on how to fill your students full of confidence that you know what you're doing. Oh well, I didn't go to that. Right, so on the next page, this is essentially nearly all of atomic physics that we need to know, and then we're just going to play with it for a long time. So we've got the quantum number n equals 1. So what values can L take? L has to be less than n. Hey, L has to be less than n. So what can it be? It can be none. And because this was done ages ago, we have to give everything names, because the chemists did this. Ooh. So this is called a 1s state. That's what the chemists call it. In fact, that's what the physicists call it as well. That's why I single out chemists. 1s state. 1 because the principal quantum number is 1, and s because L equals 0. We'll write this down a few times just to make sure that everybody's figured this out. And this is what the radial wave function varies as. So there's a normalization factor that I've not written in for all of these. I just want you to get you the shape of them. In fact, you are going to figure out the normalization factors for these things. So it goes as e to the minus r over a naught, just as we guessed. But we can also have n equals 2. The next one up, the next quantum number. So L could be 0 or L could be 1. In which case, if it's 0, if it's 2, 0, we call that a 2s state. And if it's a 2, 1, then we call it a 2p state. So this is the 2s state. So again, we have this exponential term to kill our wave function off. But now we have something a little bit more interesting here. So at some value of r, we're going to get a node. This little term here is going to go to 0. So we're going to get a node at, well, you can work it out, whatever that is, 2a naught. For the 2p state, so 2, because the principal quantum number is 2, 1 corresponds to p. People call it a p. And we have an exponential term, again dying off, and we have an r term at the front. That's the way the solutions come out. What about n equals 3? So then L could be 0, 1, or 2. So we're going to call that 3s, 3p, and then if L equals 2, we're going to call it 3d. So again, we have exponentially dying wave functions, but these are slower now. So for the 1s state, it dies off as 1 over a naught. For the 2 states, it goes as 1 over 2a naught, so it dies off twice as slowly. This one is 1 over 3a naught, so it dies off 3 times as slowly. So these are bigger, those are middle, and that's small, depending on this exponential decay term. This one's going to have a node. This one's going to end up having 2 nodes now. It's going to be 2 places where this bracket will go to 0, and it will kill off any chance of ever finding the electron. So here's ones I sketched earlier. So when you go home on Sunday morning, Sunday afternoon, with your graphics package that you like to use to plot things, have a play around and plot these things and see what you think of them. So this is the 1s state. So it's just the one that we've done. So the radial wave function dies off exponentially, but the probability, the radial probability distribution has a peak at r is equal to a naught. So the most probable place to find my electron is here. And if I integrated this up to 90%, when I got to about here, there's a 90% chance I'm going to find it somewhere within this region around where my proton sits. Go to the next one. There's a line across there, which you can't see. So now if I draw this for the 2s state, that's the black curve. So again, it goes up, so at the origin, that particular wave function is high, the same way as the 1s up here is high, whereas the 2p state has got 0 wave function at the origin. It crosses the line here, so when you square this up, I'm going to get a node. So the corresponding radial distribution function has a little bump corresponding to this bit up here. Then we have it crosses the axis, so we're going to get a node, and then we have our big bump again. So this is the 2s state. There's in fact 2 concentric rings. You're most likely to find it at some ring. Got your proton here. You have a ring around it, a sphere, and then you have another little sphere here, this little bump. That's where you're going to find it. So you can actually find it very close to the core because of this little bump. What about 2p? 2p has this shape, whatever it is. And then you square it up, multiply by r squared, and we end up with this nice big function, which is a little bit further out than the 1s state. So the 2s's, the 2s and the 2p, are a little bit further away from the core than the 1s because of the exponential term getting slower. And you can do that for 3 as well. In fact, for 3, it's a bit more interesting. So for 3 now, these are what the wave functions look like. They're doing all sorts of stuff. Square them up, multiply by r squared. So the 3s, we're going to get a little bump, a node, a bump, a node, a big bump. So for a fixed value of n, so we take n equals 3, to get near the core, the s state has got most chance of being near the core. Then the p state, and eventually the d state is this big lump out here which doesn't really get near the core at all. Even though the maximum gets, this is the maximum for s, for p, or for d, or for l equals 0, 1, and 2, the maximum gets further away. This little bump gets closer. So the s state, even though it's bigger and fatter than everybody else, has this tiny little bit at the core with this little bump. So that's going to become very important later on when we look at multi-electron atoms. So the little figure at the bottom, you can hopefully just about see, we can zoom into it. Whoa, there we go. So this should be, do like that, hang on. The one at the top is a 1s state. We just get this sort of ring around it. This one is a 2s state, so you get the ring, which is a bit fatter than that one, plus a little core. And this one is the 3s state, a bit fatter than all those, plus another ring, and plus right at the center, you can't see it, another small ring. So this is actually the sort of projection of the radial distribution into 2 dimensions. So we're going to say some things about these in general. Oh, and then we will look at the full solutions. So what are we actually going to say about them? We can work out how many nodes they have. Whoa! How many nodes do they have? So they have n minus l minus 1 radial nodes. This is on page 15, just the previous page. Which you can see from the figures. So for a given value of L, if we fixed L, as n increases, the electrons found further away as n increases, on average. So you've got the 1s, then the 2s is a bit fatter, and the 3s is a bit fatter than that. On average, that's where you find it. Even though you've got this little bump near the core, on average, that doesn't matter too much. It will matter when we consider multi-electron atoms. What else can we say? If we fix the principal quantum number, the electron is more likely to be found really quite close to the core for small l. So even though you've got 3D on average is that big, 3p is a little bit bigger, and 3s is a little bit bigger than that, if we just looked at right near the core, the 3s has got this little bump, so you're more likely to find an electron very near the core for 2s than for 2p than for 2d. So there's a play between, on average, where do you find it, and just around the core, what's the probability of finding it. That's one of the take-home messages of this section, which we will come back to later on. Okay, so now we stitch them all together. How many quantum numbers do we have? We have 3. We've got 3 labels for our electron now, and that's all we need to know. Once we know that, we know nearly everything about our electron. So we have the angular part, which we wrote down as a function with quantum numbers L and m sub L. Those are the 2 things you need to know to pick out which eigenfunction you were going to use. And for the radial part, you've got a radial wave function that depends on n and L. So L was in there, and we've introduced this new quantum number n. So it's an old one that we've seen before, but anyway. So they all have names. N is the principal quantum number. In fact, that one governs energy, just as it does for Bohr. So it's essentially the same n that Bohr had, and that governs the energy of the situation, the principal quantum number. L has the name orbital angular quantum number. And m sub L we're going to call the orbital magnetic quantum number. So in section B, after this, we'll be playing with L and m sub L a lot. And you'll see why we're going to call these orbital angular and orbital magnetic quantum numbers. So not only do we have these, so I could now tell any of you, I have an electron in the n equals 4, L equals 2, m sub L equals -2 state. And you can now draw me a picture of exactly what its wave function looked like, what its probability distribution looked like. You could tell me everything I ever wanted to know that we've discussed about the shape of the wave function, just from knowing those 3 numbers. I don't have to tell you anything else. Quantum numbers are very powerful in that sense. So we can write our wave function now as it's a wave function, but I need to tell you what n is, I need to tell you what L is, and m sub L. Because I've got R of n and L, and I've got the angular wave function of L and m sub L. So we're getting more abstract now. We're getting away from writing down masses of cosines and exponentials and all sorts of stuff. Eventually, we just want to write down quantum numbers and play with them without any actual sines, cosines, exponentials. All right, yeah, and then we've got the names. So if L equals 0, that's got the name an s orbital. If L equals 1, we call that a p orbital. If L equals 2, it's a d. And if L equals 3, which we never get to, it's an f. So they have names as well as numbers. Sorry.
Is 5.1 a sum or a product?
Product. It's R times L. So R times big Y, sorry. So the radial wave function times the angular wave function is going to give me the total wave function. Just as we wrote there a long time ago, yesterday. Okay, so let's ask a question. How many electrons can actually fit in these quantum number states? So I've drawn these nice pretty pictures, so the question is how many electrons can I fit in each quantum number state? Can I just shove as many as I want to? What happens? So say I don't have just hydrogen, I now have potassium, which means I've got 17 electrons. What happens to those 17 electrons? Can they all just stick into this lowest energy state, this 1s state? What happens to them? Well, you all know that doesn't happen. We have the Pauli principle. What does Pauli say? Pauli says, no, 2 electrons, and I missed this bit out, on the same atom can have the same quantum numbers. No 2 electrons in the same atom can have the same quantum numbers. So we're labeling them with n, l, and m sub l. That might mean that we can only fit 1 electron and n equals 1, l equals 0, m sub l equals 0, and then the next electron has to go somewhere else. But there's a degree of freedom that we haven't written down yet. There's another degree of freedom for our electrons called spin, which is another quantum number. We're going to get another quantum number out of spin, but it only has 2 possible values. It doesn't depend on anything else. It can be basically spin up or spin down. So if we want to write down all the quantum numbers for any electron, I have to tell you n and l, I have to tell you m sub l, and I have to tell you whether it's spin up or spin down. And then Pauli is happy with me. So I can have n equals 1, l equals 0, m sub l equals 0 spin up. I can have n equals 1, l equals 0, m sub l equals 0 spin down. So I can now fit 2 electrons in any of my quantum states, in any of these orbital states. And we're going to draw these out explicitly on the next page. So, n equals 1, l must equal 0, because it's got to be less than n, m sub l is also 0. So that's called a 1s state. So the energy we now know is minus 13.6 electron volts. It's one state, and that can take 2 electrons. I can fit 2 electrons in there. For the n equals 2, I can have L equals 0 or L equals 1, which means my next quantum number, m sub L, could be 0, or it can be 1, 0, or minus 1. What do we call them? If it's got no, if L equals 0, we're going to call it 2s. If L equals 1, it could be 2py, 2pz, or 2px. So we've got p because of the L quantum number, and then we've got x, y, or z to denote which m sub L it is. So there's 2 different ways of writing it down, with letters, 2px, or with quantum numbers. And we know what the energy is. It's minus 13.6 divided by 4. We've got 4 electronic states, which means I can fit 8 electrons into the n equals 2 shell. Yes, hello.
Does the radius with which the electron state not influence its energy then? Like if it's in a certain state, it's good with the nucleus.
So, good question. So, you start off from the Schrodinger equation, which is the energy operator, acting on the wave function to give you the energy plus the wave function back. And so in the first one that we did with L equals 0, the angular bit just dies off and we're just left with the radial component. So you could just write down that the radial component is the wave function. In which case that then tells us, as the wave function, the energy operator is things to do with the kinetic energy and the potential. So now we know where our electron is. We've got this wave function which tells us we're going to find our electron lots here, none here, or the probability distribution being the other way around. So there's a unique energy associated with that state. So for the n equals 1 state, we're going to get minus 13.6. For the n equals 2, minus 13.6 over 2 squared. So if you take the form, so we now know the mathematical form for the 2, 1, 1. You can now look it up in a book, you can find all the mass, you can plug it into the Schrodinger equation, churn it all around, and you will find it comes out as minus 13.6 over 4. So n governs the energy. What about the 3s? Let's do the 3s. N equals 3. I can have L equals 0, L equals 1, or L equals 2, which means I can have M sub L equals 0, or M sub L equals 1, 0, or minus 1, or 2, 1, 0, minus 1, minus 2. There we go. So I think there's a problem on the question sheet, which is it an eigenfunction? What's its energy? Hello? No, it's the connection between these and these is a bit arbitrary. Because you have to define x, y, and z in space, and I can define x, y, and z anywhere I want, so it's an arbitrary notation. But the 5 of these correspond to the 5 of these. But it's not a one-to-one correlation between them. There's not 2 is this one, and, oh, sorry, 2 is this one there. Don't worry about that. So what's the energy? It's minus 13.6 divided by 3 squared, which is 9. How many states have I got? 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 9 states, so I can fit 18 electrons in there. So now we can make some sense of what do we do if you have lots of electrons. Say we had lots of them. Electrons like to sit in the lowest energy states. I've got 2 electrons. They're both going to go into the 1s state, because that's got the smallest, the lowest energy. If I've got any more electrons, they're going to go into the n equals 2 state, so they're going to fill up these ones. It doesn't care which one it fills up because they're all got the same energy. So I can fit another 8 in there. So that's 10. If I've got an 11th electron, it's going to stick somewhere in these in here. So I now know the energy ordering of these states. What do they look like? So we've drawn all these a few times. But this is now the angular dependence and the radial dependence combined. So the 1s is a tiny little sphere hugging the origin. The 2s is a bit fatter. The 3s is fatter still. Then we've got the dumbbells for px, py, and pz, depending on how you draw space. Then for the 3s, we have the px, py, and pz that look like dumbbells. And for the 3ds, we have crazy stuff that look like this, with all their nodes and angular dependence. So you've probably drawn most of these down. Say pajamas if you've ever drawn things like this. Okay, hopefully that was all of you. Hello.
Hi, are we claiming that for principal quantum number, the s orbitals and the p orbitals have the same energies?
Yes.
So that's wrong.
No, not in this regime, because I've not coupled my angular momentum with my spin angular momentum. But we will do in the spin orbit chapter, yes. In this regime, this is correct. There's more shenanigans that goes on when we include spin. Spin is another form of angular momentum. Schrödinger has nothing to say about spin, so that's why it's not appeared. It isn't in there. When we discuss spin, spin will then have to add in. We have 2 sources of angular momentum, and they interact with each other, which gives you spin orbit coupling, which splits the energy states. We will do that in a couple of weeks. Good question, though. So you have hopefully drawn most of these down. So just from considering solving the Schrödinger equation with certain boundary conditions, with the conditions that it's got to be, the solutions have got to be finite, splitting it up into the angular component, the radial component, we get all this beautiful work that describes how electrons really behave around atoms and their shape, in fact. If you go down to my lab, we image pz orbitals of silicon all the time. And we can see them pointing straight up and we get nice bumps. Sometimes we can put a d orbital, let's pick a d orbital on the end of my scanning tunneling microscope tip, and if you angle it around, you're going to have 2 bumps like this, and we can see that we get 2 little bumps. We basically image that and that. 2 tiny little bumps, because that's the way the Schrödinger equation is solved on the end of an atom, or on an atom. It's quite magical. And we've got 5 minutes left. Excellent. So let's keep going. How do we actually measure any of this? So we've only talked about energy so far. Here's a color version. So this is an absorption spectrum from the sun. So the next time the sun's in the sky, get a telescope, point a telescope at the And the next time the sun's in the sky, get a telescope, point a telescope at the sun, get a diffraction grating, diffract the light onto something. And so we got red light with long wavelength, blue light with short wavelength, and you find all these black bands, bits of light which is missing. So we don't have a continuous spectrum. If you consider the sun as just a black body emitter, then we should just have a continuous spectrum of light with some shape to do with, is it Stefan Boltzmann? Something like that, whatever it is. But we see these lines, we see these black lines. So what it is, you've got the sun here with light, doing whatever light does. Then you've got some sort of like gas and stuff in the sun itself. Then we've got us over here with our spectrometer. So as the light comes along, it has to pass through atoms, it has to pass through gas, it has to pass through the sun itself. And sometimes the energy of the light that hits an atom, it's just got the Goldilocks energy to take an electron from n equals 1 to n equals 2. If it's got exactly that right energy, 13.6 minus 13.6 over 4, whatever it is, that atom can absorb that light. So therefore, it's now going to be missing from the light that we see, because the atoms have absorbed it. And from all this, you can actually work out the elemental constitution of the sun. Each of these corresponds to a lithium atom or a hydrogen atom or a certain transition, and we can map down exactly which is which. And back in the day, what does that mean? Like 1901 or something like that, or even earlier, people were looking at the spectra from the sun, and they realized that there were some lines here they couldn't account for. And so they invented a new atom called helium, Helios being, was that the god of the sun, or the son of the god? So the first time anybody ever invented helium, or not invented it, for God's sake, any time anybody discovered helium was in the sun, from looking at atomic spectra like this. Outstanding. So, how do we actually get atomic spectra? Whoops, wrong one. I'll give you the answers, that'd be too easy, I could just go home. So, how do we get them? So we want to measure the energy of the electronic states. Because at the moment, that's the only thing which we know differentiates our electronic states. Minus 13.6 electron volts, or minus 13.6 divided by 4, or minus 13.6 divided by 9. So we're going to do spectroscopy. So we can do emission spectroscopy. We're going to excite our atom, take our electron from the ground state, from the n equals 1 state, bung it somewhere very high up. Eventually it'll drop down, it'll emit a photon. So we excite into a high-lying state, it then relaxes, and it emits a photon with a very precise energy based on the energy difference between those two states. You can't have any old energy. It has to be 13.6 divided by 4 minus 13.6, or the other way around. It has to be that energy difference. Not a little bit more, not a little bit less, because there's nowhere for the electron to exist around my hydrogen at 13.5. Doesn't exist, doesn't solve the Schrodinger equation, can't do it. How do we excite things? Thermal excitation, that's what happens in the sun, it's just like damn hot. So you've got half kT's worth of energy, and eventually a half kT gets up to being 13.6 electron volts, so you can excite the electron anywhere you want. In a sodium lamp, you create plasma. Or we can do collisions. So I think the very final thing we're going to do is look at the helium-neon laser, where we're going to excite helium, and that's going to pass excitation onto the neon, and that's going to give us lasers. So there's lots of ways that you can create excitation. And the other one, the one that we just looked at, in fact, is absorption. So absorption spectra. So we're going to absorb light with a very precise energy, promoting an electron from one energy state to a higher energy state. Light comes in, it's going to take my electron from n equals 1 to n equals 2, or from n equals 1 to n equals 3, or from n equals 2 to n equals 3. But there's well-defined energies, and it only absorbs well-defined wavelengths of light. And that's why in the absorption spectra we get these black missing lines. It tells us what the chemical constitution of the universe is. Go and shine your telescope at a galaxy. You can now measure exactly the chemical composition of the galaxy. And with that, I'll see you on Wednesday.